Okay, guys, let's walk through mini quiz number 4. Answers to the 4 multiple choice questions are right here, A, C, and C. Let's walk through there and see how we did on each one of them. Okay, so for the first one, they told us that the function f is continuous on a closed interval from 2 to 4, twice differentiable on that open interval. So both its first derivative and its second derivative exist at every x value between 2 and 4. They tell us now that the value of f prime of 3 is 2. So if we stop there for just a second, we've got a value of our derivative here in the middle of our interval, and it's positive. So the first thing we see right there is that when a function's derivative is positive, it has to be increasing as we're moving from left to right. So I'm wondering if we couldn't rule out any of these 5 choices right off the bat, but unfortunately, it looks like all of them are strictly increasing functions with no decreasing throughout that. So no such luck there. The second thing they tell us right here is that the second derivative is going to be negative on this open interval from 2 to 4. So putting these two things together, we know that our function is increasing, but we know that it's increasing at a decreasing rate, meaning that it's increasing but concave down, looking something like that. So increasing at a decreasing rate is what we're looking for here. Okay, so if we take a look at the 5 choices right here, there's one of them that jumps out to me right away, and that would be D. And as we take a look at D, our x values jump from 2 to 3 to 4, and the corresponding y values go from 3 to 5 to 7. And if we look at this in terms of what kind of function we're dealing with, we can see that the increase from 3 to 5 is 2, and from 5 to 7 is 2 also. What we're dealing with right here in D is a linear function, because it's increasing at a constant rate. We were looking for one increasing at a decreasing rate, so we know right away that the answer is not D. Okay, let's take a look at some of the other ones then and see if we can't figure out that same thing then, looking at it the same way. As we look at A, our y values jump from 2.5 to 5, so that's an increase of 2.5, and then an increase of 1.5 after that. So we see that the function is increasing, but it's losing steam. A could definitely be a possibility for the answer here. Let's take a look at B. From 2.5 to 5 is an increase of 2.5, and from 5 to 7 is an increase of 2. Same thing, the answer could be B. Unfortunately here, boys, C, we have an increase of 2 followed by an increase of 1.5, so it could be C. If we take a look at E, from 3.5 to 5, we increase by 1.5 and then by 2.5. E is one we're going to have to throw out because E is a function that's increasing at an increasing rate like that. So we're down now to 3 possibilities. And the one thing that we haven't really paid any attention to yet is that they didn't only tell us that the first derivative was positive, but they actually gave us the value of that first derivative at 2. Okay, now what we know here is that on this particular interval right here, starting at 2 and ending at 4, the value of its derivative has to equal 2, or in fact it does equal 2, somewhere inside that interval. This gets me thinking about the mean value theorem and what the MVT tells us then about the existence of a derivative here. So if we think about part A right here, and we tried to evaluate the average rate of change right here, and I did it as a y2 minus y1, sorry guys, over x2 minus x1. Let's see what happens here. The 6.5 minus 2.5 gives us a 4 on top. The 4 minus 2 gives us a 2 on bottom. So our average rate of change, or the slope of our secant here for A, is 2. That guarantees now, because this function is continuous and differentiable on the interval from 2 to 4, that guarantees us that the value of the derivative of this function must equal 2 at least once, somewhere in the interval then, from 2 to 4. So that is definitely something that's interesting, and that might be correct. If we tried the same thing here on B, let's do that same work here on the average rate of change. The 7 minus the 2.5 right there is going to get us a 4.5. The 4 minus 2 is going to get us a 2. That only guarantees that our first derivative would have to equal 2.25 at some point. That doesn't guarantee that the derivative has to equal 2. And I think the same thing happens here on C. 6.5 minus 3.5 is an increase of 2.5 over 2. I'm sorry, that was 3.5 over 2, and that gets us a 1.75. We were looking for a function here whose average rate of change was 2, which would guarantee that the instantaneous rate of change would have to work out there as well. So because A is the only one that gives us that average rate of change that we were looking for, A is the answer to this one right over here. All right. Let's take a look at number 2. What do we have going on right here? In the xy plane, the line x plus y equals k, where k is a constant, is a tangent to the graph of y equals x squared plus 3x plus 1, and they want to know the value of k. Okay, so let's play around with that a little bit. Well, we're talking about tangents here. We're talking about a line right here. Probably slopes are going to come into play here, so I'm going to go ahead and take the derivative of y with respect to x and get it as 2x plus 3. Now, we know that we have a tangent line right over here of x plus y equals k, and I'm going to go ahead and rewrite that in slope-intercept form as y is equal to negative x plus k. That tells us that the slope of our tangent of this particular line here is the coefficient of x, which is going to be negative 1. So we know that this derivative here, evaluated at this particular point, has to have a value of negative 1. That should tell us then what the x value is at the point of tangency. Subtracting the 3, we're going to get a 2x is equal to a negative 4, and then from there we'll divide by 2 and get x equals negative 2. Now it doesn't surprise me, guys, that negative 2 is one of the 5 choices for this problem here, but that is not the question that they were asking. They wanted to know the value of k. All we've come up with here is the value of x. So to do that, we're going to eventually go back to this one equation right here, the only one that contains a k in it, but I also need to know what y is. So let's go to the original function right here, guys, and let's go ahead and evaluate y when x is negative 2. The negative 2 squared is going to get us a 4, then a minus 6 plus 1. So y of negative 2 is going to get us a y value of negative 2 plus 1 is negative 1. So we're dealing with the ordered pair negative 2, negative 1 for our point of tangency. And now, probably should have switched colors a while ago, let's go back to the equation of our tangent line right over here, and now that we know the values of x and y, x is negative 2 plus a y value of negative 1, that should get us the value of k here. K looks like it's going to be negative 3, and our answer here for number 2 is A. Moving right along to problem number 3, getting into the calculator questions right here. Although looking at the answers, I don't see a whole bunch of decimals, so I'm not sure that I'm going to need the calculator here or not. The radius of a sphere is decreasing at a rate of 2 centimeters per second. Okay, guys, I think I know where we're going already. We're looking for, let's see, at the instant when the radius of the sphere is 3, we want to know the rate of change in square centimeters per second of the surface area of the sphere. Okay, guys, so what I'm hoping we recognize this as right away is a related rates problem. And that's where we're at. So the way we usually begin a related rates problem is to talk about a derivative that we know and a derivative that we want to know. And they tell us right at the beginning the radius of a sphere is decreasing at a rate of 2 centimeters per second. So the derivative of our radius taken with respect to time. Now this is a little tricky because they tell you the radius is decreasing. That actually means that our derivative has to be a negative 2 centimeters per second. Now, it looks like all 5 answers are negative, which makes sense. Since the sphere is getting smaller, its surface area is going down as well, but I could see people making a mistake with that. We want to know the rate of change of the surface area of the sphere. Now, they're using capital S for surface area, so we want the derivative of S taken with respect to time at the moment when, let's take a look, at the instant when the radius of the sphere is 3 centimeters. Okay, my guess is that that means that the surface area is not decreasing at a constant rate. Okay, so we know dr dt. We want to know ds dt. That means that we need an equation that relates r and s together. And lucky for us, they gave it to us right there. Surface area of a sphere is 4 pi r squared. And remember, guys, no matter how many of these formulas here you've learned during the course of the last umpteen years, they're not going to ask you to recall a bunch of weird and abstract formulas here from geometry. They're going to give them to you. Okay, so we are now going to differentiate both sides of this equation with respect to time. So the derivative of surface area with respect to time is going to equal, differentiating this mess, we are going to get an 8 pi r, but that's going to get multiplied now by dr dt because of the implicit differentiation. And now, everybody, what we have here are 1, 2, 3 variable quantities within this equation. We want to know the value of ds dt. That's this one right over here, so we better know the value of r at the moment in question and the value of dr dt. And I think we've got that here. Let's see what's going on. So ds dt is going to equal 8 times pi. The moment in question has a radius of 3 centimeters, and we're multiplying this by dr dt, which we said was -2. So that's a -6 times 8. Looks like our answer here is a -48 pi, and that means that C is going to be the right answer here for problem number 3. Okay, final multiple choice question here. They want an average value of a function on a closed interval. Whether we got this one right or not probably depended on whether or not we remembered the formula here for average value. And it's a pretty straightforward formula, okay? Average value of a function is given by 1 over b minus a multiplied by the definite integral from a to b of whatever function it is that you're dealing with. If you guys want to think about this another way, that definite integral right there tells you the area underneath a curve, and the b minus a here tells you the width. So what we're really doing here, guys, is we're taking area and we're really dividing it by the width of your function overall. And what that basically gets you, if you just think about a rectangle, is height, or better yet, the average height of a function on that particular interval. All right, let me get some of this mess out of here. So they wanted to know the average value of this function right over here on the interval from -1 to 3. So we're going to go with a 1 over, b is 3, minus the -1, that's a 3 plus 1, times an integral from -1 to 3 of f of x, which is a cosine of x, over an x squared plus x plus 2, all taken with respect to x. And unless something goofy happens, I'm thinking we can just dump this into the calculator here and figure out what's going on. So let's take a look at this, everybody. We are going to start with a 1 over 4, and we are going to multiply that by, here we go. Actually, there was a integral tool there, but I think I skipped it. All right, here we go. Our limits of integration were going to be a -1 on the bottom, then a 3 up on top, and the function we were integrating, let's take a look. It was a fraction, and I've forgotten already what it said. Cosine of x on top. All right, so cosine of x goes right there. And on the bottom, we had a quadratic trinomial, x squared plus x plus 2. X squared, gotcha, plus x plus 2. Okay, and we're integrating all of that with respect to x, and I would imagine that should get us the right answer here, guys, of 0.183 if we were going to round that. All right, 0.183, and C is going to be the right answer. Now, I wouldn't be shocked at all, everybody, if this, there we go, this part right here was something that people forgot to put in their calculator. It wouldn't surprise me at all if you guys wrote it down on your paper, but then kind of got blinded by the light and only put the integral in there. Now, what that quantity did is it allowed me to take the value of this integral and divide it by 4. So I would think, everybody, that an answer some of you might have come up with would have been the correct answer, but multiplied by 4, which is 0.732, and sure enough, that was one of the choices right there. I don't remember off the top of my head how many of you guys chose that one, but anyway, not surprising that that one showed up. Okay, let's transition into the free response question. And you guys did pretty well on this one, although, I got to be honest and tell you guys that when we take these mini quizzes in class year in and year out, people don't do all that well on them. And you guys are definitely doing better than most people tend to do normally, which makes me think some of you guys are just Googling answers right here. But anyway, let's take a look at what's going on. I like this one a lot. 700 people are in line for a popular amusement park ride right when the ride begins operation in the morning. Okay, so they open up the gates at Walt Disney World. Everybody floods in before they even start Space Mountain. Okay, so 700 people get in line and then they turn the machine on. Once it begins operation, the ride accepts passengers until the park closes 8 hours later. Well, that's BS. Any good amusement park is going to be open a lot longer than 8 hours. But anyway, while there is a line, people move onto the ride at a rate of 800 people per hour. Now that phrase right there is a little bit funny. That 800 people per hour is the rate at which people move onto the ride, but what it really means is that's the rate at which people are leaving the line. And if we haven't figured this out already, guys, this is yet another input-output problem right here. People are coming into the line at a rate according to this function right over here, and they're coming out of the line at a rate of 800 people per hour. I don't know this for a fact, but my guess is they do some mathematical analysis and they know what the capacity of rate is in a particular ride. And one of the things I would think that amusement parks would try to do would be to try to maximize the number of riders per hour they can get in on their rides. Okay, so this function right here, R of t, is your input function. It tells you how quickly or at what rate people per hour people are showing up for the ride itself. Okay, so here we go. Let's take a look at part A. How many people arrive at the ride between t equals 0 and t equals 3? All right, guys, now a few of you kind of missed the boat on this one right here. The function we're looking at, R of t, is measured in people per hour. What we want to know is how many people arrive at that ride there. So the way to go from a people per hour rate function to the total number of people would be to integrate that. So they wanted us to evaluate an integral from 0 to 3 of this R of t function taken with respect to t. So without an explicit definition of R of t, we had to just say, all right, starting at 0 right here and ending at 3, we're going to evaluate the integral here by using geometry. All right, and what most of you guys did is you kind of split this thing right here at 2, and you found the areas of 2 different trapezoids added together. So the first trapezoid would be 1/2 times a height of 2. Again, we're moving horizontally here, and the sum of its 2 bases would be 1,000 plus a 1,200. Okay, that'll get us the area of the first trapezoid. And then we would add to that the area of the second trapezoid. That would be 1/2. Here your height would just be 1, and your 2 bases right there would be a 1,200 at the beginning at t equals 2, and then dropping down to an 800 at t equals 3. Okay, so the 1/2 and the 2 here just cancel out, all right? So the 1,000 plus the 1,200 is going to get us 2,200 people arriving at the ride between 0 and 2. Then 1,200 plus 800 is going to get us 2,000, and half of that is going to be 1,000 people who show up between the times of 2 and 3. So the total number of people that show up from 0 to 3 hours is going to be 3,200 people showing up there. Okay, so that takes care of part A. Let's move on to part B now. Is the number of people waiting in line to get on the ride increasing or decreasing between t equals 2 and t equals 3? And of course, we have to justify our answer here. Okay, a lot of people really overthought this one right over here. Let me go ahead and erase some of the gobbledygook that I put on that graph right there, and let's take a look at what's going on. It's all a question of people per hour, everybody. And what happens is that this graph right here that they gave us for R of t tells us the rate at which people are getting into the line. But right here, at a nice constant rate of 800 people per hour, that's the rate at which people get out of line or get onto the ride itself. Now, the important thing, or the important time I should say, is right here at t equals 3. At that one moment, and only at that one moment, the rate at which people are being added to the line and the rate at which people are being taken out of the line are exactly the same. So at that one moment, the line isn't getting any longer or any shorter. It's staying exactly the same. So then we have to think about what happens around that time. Now, prior to t equals 3, which would be here and here, what we can see is that our r of t value is greater than the 800, the rate at which people were getting out of line. And every time after t equals 3, now this r of t function dips below. That means that for most of the day here, people are showing up for the line here at a rate slower than they're getting on the ride and getting out of line. So the maximum possible time here for people in the line is going to happen right here. Prior to t equals 3, the line was growing because r of t was greater than 800. After that time, r of t is always less than 800, so that line is always going to be shrinking. So to answer this question right here, is the number of people waiting to get on the line on the ride increasing or decreasing between 2 and 3? Well, from 2 to 3, we're talking right here on this interval. That is still above that 800 right there. So the answer is going to be increasing. So what would we say here, guys? The number of people in line, try to be efficient here, is increasing. Okay, between t equals 2 and t equals 3. And our justification here would be because r of t is greater than 800 people per hour on, I wanted to write on this interval. It sounds a little silly to write it again, but it's actually more efficient to be specific and just use mathematical notation and say on that interval from 2 to 3. So we clearly answered the question, increasing, and we gave the reason here because r of t is greater than 800. As it worked out, you guys didn't know this at the time, all of b was only worth 1 point. So to get that 1 point, you needed to have the answer increasing, but also the reason because r of t was greater than 800. Let's take a look at part C here. At what time t is the line for the ride the longest? And how many people are in the line at that particular time right there? Okay, all right. So this actually harkens back to what we were just talking about here in example in problem B. So we knew here that from 0 to 3, the rate at which people were getting into the line was exceeding the rate at which people were getting out of the line. And then later in the day, that changes and that flip-flops at t equals 3. So let's read part C again. At what time t is the line for the ride the longest? So let's take a look at what we had right here. So I think we can say here the line is longest at t equals 3. Now they did ask us to justify our answers right there, so I think we better explain why. So the line is longest at t equals 3 because that, no, that sounded a little vague right here, so let me be a little bit more specific. Because r of t, we would say, is greater than 800 for t is less than 3. But r of t is then less than 800 for values of t that are greater than 3. So I think that kind of explains it there. They also want to know how many people are in line at that time. So the number of people at t equals 3 is going to be equal to, and guys, this question shows up on almost every input-output problem. So we talked about it a little bit before, but let's hit it again. There are 3 fundamental things that you have to consider when determining the volume at a particular time of an input-output problem. The first thing you have to worry about is the starting amount, and they almost always throw this at you, and it's really easy to miss and overlook, but they tell you there are 700 people in line when the ride begins operation in the morning. So that tells us that we're starting this thing with a total right here of 700 people. The second thing we have to consider is how much has been added to that amount. So back to this here, at t equals 3, we now want to know how many people have shown up for the ride, not at the very beginning of the day, not the initial 700, but between the times of 0 and 3. So we would do that by doing an integral from 0 to 3 of your rate of input function. Okay, so the integral from 0 to 3 r of t dt. So you have to consider how much was there at the beginning, how much you've added, and the third thing to consider would be how much have you taken out. So we would now need to subtract from this amount here the total number of people that have gotten out of line and onto the ride in between 0 and 3. Well, they told us in the problem that that rate was a constant 800 people per hour. All right, and this has been happening for 3 hours now from t equals 0 to t equals 3. Okay, so that's the way we would set this one up right here. So we've got a 700 plus, well, this is the exact same computation that we did back here in part A. The number of people who showed up between 0 and 3 hours is 3,200 people. So we're going to add 3,200 to the 700 who were in line at the beginning of the day. So up until t equals 3, a grand total of 3,900 people have shown up to get in line here total. But during that whole time, the ride has been running, and we've been able to take 2,400 people out of the line by getting them onto the ride. So that 3,900 minus the 2,400 is going to get us a total right here of 1,500 people who are still in line for the ride at this time of t equals 3. That sounds like a ridiculous number of people to me to be in line for a ride, but I guess if you've been to a big park and you know how long that can take and how many people they cram in there, I guess we can buy that. All right, let's take a look at D. Write but do not solve an equation involving an integral expression of r. That's important right there. We'll come back to that in just a minute. An integral expression of r whose solution gives the earliest time t at which there's no longer a line for the ride. Okay, so what's going on right here is this is actually a direct extension of the work that we just did here in C. We came up with a function right here that told us the total number of people in line for the ride at a particular value of 3. We now want to do the exact same thing here, but we just want to make sure that this total number of people is going to eventually equal 0. So we have to consider the exact same 3 things again, guys. For the total number of people, we have to worry about our beginning value, which is 700. Now we're going to add to that, everybody, an integral that starts here at 0, but we don't know what the time t is that we're looking for. So we'll go ahead and put t right here as the upper limit of integration. And we're going to be integrating that r function. Now, what a lot of you guys did that was technically incorrect in your work, I don't think they would take off for this, but a lot of you guys wrote this, r of t dt. And the mistake you made right here is that you used one variable here for the upper limit of integration, and then you used the exact same variable again within the integrand and the variable of integration. And we're not supposed to do that. So this is when you will see them with some frequency here, guys, simply change the variable. Okay, instead of r of t, you could literally pick any other letter that you wanted to use here. Now, I think in their scoring standards, they did an r of s, but it makes absolutely no difference there whatsoever. So this integral from 0 to t of r of s ds is going to tell us the total number of people who've been added to the line from 0 until t. And then we need to subtract from that 800 people per hour. Well, how many hours are we talking about? We don't know. That's what the variable t is representing. So we'll go ahead and multiply that 800 by t, and the most important thing, not about the most important thing, but we have to make sure then we wanted there to no longer be a line for the ride. So we'd have to set that equation equal to 0. And that should do what they wanted here, guys, right? But do not solve an equation involving that integral expression of r, got it, whose solution gives that time t. Yep, that's what we needed for part D. Okay. All right, guys, so that's a wrap. I'm going to scroll through their solutions here, and I'll keep one of them up for just a second. You guys can pause the video and take a look at that if you want to try to figure out their scoring systems. And we're in pretty good shape. What a couple of you guys did that I wanted to mention right over here, a couple of you guys made this as a 700 plus an integral from 0 to t. And some of you guys, and I kind of like this, you did the input function, r of s, and then minus the output function, which was 800 people per hour, and you included that 800 within your integral. That's absolutely fine, because when you integrate that minus 800, that just gets you the minus 800t. So either way you wanted to do that worked out perfectly fine.